The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
I guess, if people show up, they will stop. Just get going. Okay, I guess, should I introduce you?
If you want, I can introduce myself.
Kuszmaul, who's been doing a lot of work on Cilk, which is a very interesting parallel language that actually combines a lot of practical aspects and also a bunch of theoretical aspects you can say about the program. So I think it's a very interesting project that's becoming, this has been there, the Cilk had been there for a while, a lot of interesting things got developed, but I think with advent of multiples, I think it has becoming very important at this point.
So how many of you people have ever heard of Cilk? Have used it? Okay, so those of you who've used it may find this talk old or whatever, but so Cilk is a system that runs on a shared memory multiprocessor. So this is not like the system you've been programming for this class. In this kind of machine, you have processors which each have cache and some sort of a network and a bunch of memory. And when the processors do memory operations, they are all on the same address space, and it's typically, the memory system provides some sort of coherence, like strong consistency or maybe release consistency. We're interested in the case where the distance from processors to other processors and to processors to memory may be non-uniform. And so it's important to use the cache well in this kind of machine, because you can't just you can't just ignore the cache. So the sort of the technology that I'm going to talk about for this kind of system is called Cilk. Cilk is a C language, and it does dynamic multithreading, and it has a provably good runtime system. So I'll talk about what those all mean. Cilk runs on shared memory machines like Suns and SGIs, and you probably can't find alpha servers anymore. It runs on SMPs that are in everybody's laptops now. There's been several interesting applications written in Cilk, including virus shell assembly, graphics rendering, and body simulation. We did a bunch of chess programs because they were sort of the raison d'etre for Cilk. And Cilk, one of the features about Cilk is that it automatically manages a lot of the low-level issues. You don't have to do load balancing. You don't have to write in protocols. You basically write programs that look a lot more like the ordinary serial programs, instead of saying, well, first I'm going to do this, and then I'm going to set this variable, and then somebody else is going to read that variable. That's a protocol, and those are very difficult to get right.
You guys have one of the best chess programs at the time?
Yeah, I'll mention that a little bit later. We had award-winning chess players. So to explain what Cilk's about, I'll talk about Fibonacci. Now, Fibonacci, this is, just a review in case you don't know C. You all know C, right? So Fibonacci is the function that's, each number is the sum of the previous two Fibonacci numbers. And this is an implementation that basically does that computation directly. The Fibonacci of n, if n is less than 2, it's just n. So Fibonacci of 0 is 0 and 1 is 1. 2, the Fibonacci's, well, then you have to do the recursion. So you compute Fibonacci of n minus 1 and Fibonacci of n minus 2 and sum them together, and that's Fibonacci of n. One observation about this function is it's a really slow implementation of Fibonacci, right? You all know how to do this faster. How fast can you do Fibonacci? You all know this. Ooh, okay. So how fast is this one? So for those of you who don't know, you sort of know how to compute Fibonacci in linear time just by keeping track of the most recent two, right? So 1, 1, 2, 3, 5. You just do it. This is exponential time, and there is an algorithm that does it in logarithmic time. So this implementation is doubly exponentially bad. But it's good as a didactic example because it's easy to understand. So to turn this into Cilk, we just add some keywords. And I'll talk about what the keywords are in a minute. But the key thing to understand about this is if you delete the keywords, you have a C program. And Cilk programs have the property that one of the legal semantics for the Cilk program is the C program that you get by deleting the keywords. Now, there's other possible semantics you could get because, not for this function. This function always produces the same answer because there's no race conditions in it. But for programs that have races, you may have other semantics that the system could provide. And so this kind of a language extension where you can sort of delete the extensions and get a correct implementation of the parallel program is called a faithful extension. A lot of languages like OpenMP have properties that if you have these directives and if you delete them, it will change the semantics of your program. And so you have to be very careful. Now, if you're careful about programming OpenMP, you can make it so that it's faithful, that has this property. But it's not always the case that it is.
Is it okay to ask a question?
Sure.
Is it built on C89 or C99? The difference? The difference
C77. No, what is it? No, C89.
Okay,
But
so there's no presumption for any aliasing at all. It's assumed that anything can alias anything.
So the issue of restricted pointers, for example, is that,
Restricted, strict aliasing.
so Cilk is, so Cilk turns out to work with C99 as well. So
But is the presumption though for a pointer that it could alias?
the Cilk compiler makes no assumptions about that.
Okay, it's up to you as a
If you
programmer.
write a program and the back end, Cilk works, and I'll talk about this in a couple of minutes. Cilk works by transforming this into a C program that has, when you run it on one processor, it's just the original C program in effect. And so if you have a dialect of C that has restricted pointers and a compiler that
But
knows,
you're not taking any assumptions that there's aliasing. If you make a mistake,
if you make a mistake,
your
the language doesn't stop you from making a
Well,
mistake.
but in C, my own point is in C89, C89 is not a mistake. There's no assumption of aliasing, right? It could alias. So if I said,
Well,
if I spawned to,
if because of aliasing you write a program that has a race condition in it, which
it
is
would be valid
erroneous.
C without the spawn,
Yeah.
but not valid with the spawn.
No, it would still be valid. It would just have a race in it, and it would have a non-determinate result.
it won't do what you want.
It may not do what you want,
Yeah.
but one of the legal executions of that parallel program is the original C
Okay, so
program.
there's no extra.
There's very, at the sort of level of doing analysis, Cilk doesn't do analysis. Cilk is a compiler that compiles, this language, and the semantics are what they are, which is, the spawn. And I'll talk about the semantics. The spawn means you can run the function in parallel, and if that doesn't give you the same answer every time, it's not the compiler's fault. It's
I think I go from parallel to serial, not the other way around.
pardon?
There has to be some guarantee when you go from.
Even parallel to serial, that's not much of a guarantee because
Well,
parallel in
there
a race condition you get some value. Serial you get without race condition. So
All right, so one of the legal things the Cilk system could do is just run that program.
Right.
Now, if you're running it on multiple processors, that's not what happens because the other things, there's some performance guarantees we give, so there's actually parallelism. But on one processor, in fact, that's exactly what the execution does. So Cilk does dynamic multithreading, and this is different from P threads, for example, where you have these very heavyweight threads that cost tens of thousands of instructions to create. Cilk threads are really small, so in this program, there's a Cilk thread that runs basically from when the fib starts to here, and then I feel like there's some missing slide in here. I didn't tell you about spawn. Okay, well, let me tell you about spawn, because what the spawn means is that this function can run in parallel. That's very simple. What the sync means is that all the functions that were spawned off in this function all have to finish before this function can proceed. So in a normal execution of C, when you call a function, the parent stops. In Cilk, the parent can keep running. So while that's running, the parent, this can spawn off this, and then the sync happens, and now the parent has to stop. And this keyword basically just says that this function can be spawned.
is the sync only for that scope, or how about the children's scope?
The sync is scoped within the function. So if you could have a for loop that spawned off a whole bunch of stuff.
So if you call a function itself would read some spawns, but then return without doing a sync.
There's an implicit sync at the end of every function. So Cilk functions are strict. Strict. There's
But only
another
goes to you don't. It's recursive, right? So.
Yeah. Right. So there's children down inside here, but this function can't return. Well, if I had omitted the sync down in some leaf, the compiler puts one in before the function returns. So you can't. There's some languages that are like this where somehow the intermediate functions can go away, and then you can sync directly with your grandparent.
It's only for this frame because otherwise it would stop the other.
Right. So this gives you this DAG. So you have this part of the program that runs up to the first spawn, and then the part of the program that runs between the spawns, and then the part of the program that runs after this, after the last spawn to the sync, and then from there to the return. So I've got this drawing that shows that this function sort of running. So first the purple code runs, and it gets to the spawn. It spawns off this guy, but now the second piece of code can start running. So he does a spawn. So these two are running in parallel. Meanwhile, this guy started that off. And this is a base case, so he's going to not do anything. He's just going to, because I'm doing fib of 4. It just feels like there's something missing in this slide. Oh, well. Essentially now, this guy couldn't run, going back to here, this part of the code couldn't run until after the sync. So this thing is sitting here waiting. So when these guys finally return, then this can run. This guy's getting stuck here. He runs, and these runs. These two return, and the value comes up here. And now basically the function's done. One observation here is that there's no mention of the number of processors in this code. You haven't specified how to schedule it or anything, how many processors. All you've specified is this directed acyclic graph that unfolds dynamically, and it's up to us to schedule those onto the processors. So this code is processor oblivious. It's oblivious to the number of processors.
But a person using the language will probably have to write as many spawns depending on.
No, what you do is you write as many spawns as you can.
Oh.
You expose all the parallelism in your code.
Okay.
So you want this DAG to have millions of threads in it concurrently. And then it's up to us to schedule that efficiently.
Right.
So it's a different mindset than, I have 4 processors, let me create 4 things to do. I have 4 processors, let me create 1,000,000 things to do. And then the Cilk scheduler guarantees to give you have 4 processors, I'll give you 4-fold speed up.
So I guess what you'd like to avoid is creating this mindset where the programmer has to change or finds that tuning the parameters results in different performance.
So there's some tuning that you do here in order to make the leaf code. There's some overhead for doing function calls. So it's small overhead, it turns out. It's like the cost of the spawn is like 3 function calls.
Okay.
So you end up wanting to, if you were actually trying to make this code run faster, you would make the base case bigger and do something, speed things up a little bit at the leaves of this call tree. So there's this call tree, and inside the call tree is this DAG. Cilk supports C's rule for pointers, for whatever dialect you have. If you have a pointer to a stack that's, and then you have a pointer into the stack, and then you call, you're allowed to use that pointer in C, and so in Cilk you are as well. If you have a parallel thing going on where normally in C you would call A, then B returns, then C and D. So C and D can refer to anything on A, but C can't legally refer to something on B, and the same rule applies in Cilk. So we have a data structure that implements this Cactus Stack. That's what it's called, after the saguaro cactus. That's what sort of the view of the imagery there, and it lets you support that rule. There's some advanced features in Cilk that had to do with speculative execution, and I'm going to skip over those today because it turns out that sort of 99% of the time you don't need this stuff, and so I'll skip it. We have some debugger support, so if you've written code that relied on some semantics that maybe you didn't like when you went to the parallel world, you'd like to find out. So this is a tool that basically takes a Cilk program and an input data set, and it runs and it tells you, is there any schedule that I could have chosen? So this is that directed acyclic graph. So there's a whole bunch of possible schedules I could have chosen. Is there any schedule that changes the order of two concurrent memory operations where one of them is a write? So we call this the non-determinator because it finds all the determinacy races in your program. And Cilk guarantees, the Cilk race detector is guaranteed to find those. There's a lot of race detectors where if the race doesn't actually occur, you have two things that are logically in parallel, but if they don't actually run on different processors, a lot of the race detectors out there in the world won't report the race, so you get false negatives. And there's a bunch of false positives that show up. This basically only gives you the real ones.
It's not fully sound with respect to the input data. There might be still a input data that might lead to a race, but this input doesn't.
Yeah, so this doesn't analyze the program, it analyzes the execution. And so it's not trying to solve some NP complete problem or Turing complete problem, right? It's trying to, and so this reduces the problem of finding data races to the situation that's just like when you're trying to do source code release and quality control for serial programs. You write tests. If you don't test your program, you don't know what it does, and that's the same property here. You have to, if you do find some race someday later, then you can write a test for it and know that you're testing to make sure that race didn't creep back into your code. And that's what you want out of a software release strategy.
So big problem is most of the time you have a race. You need to put some any code to look at what's going on race most early. So that's
Right.
the problem with races. You have
So this will, if there, as long as the code doesn't, if you start putting in sinks and things, a sink, then maybe the race goes away because of that. But if you just put in, instrumentation to try to figure out what's going on, it's still there. The race detector sort of says, oh, this variable in this function, and this variable in this function. You look at it and say, how could that happen? And finally, you figure it out and you fix it. And then you put if you're trying to do software release, you build a regression test that will verify that that's not, that has that input.
Can you have a situation where the spawning graph spawns non-deterministically? So it's not a race, but non-deterministic spawning is there. So when you run the non-determinator, it spawns a graph in a little bit different way that has no race. But
Yes, the race detector, for example, our race detector understands locks. So part of the rule is it doesn't report a race if the two memory accesses, if there was a lock that they both held in common. Now you can write buggy programs because you could essentially do a memory, lock, read the memory, unlock, lock, write the memory, and now the interleave happens and there's a race. So the assumption of this race detector is that if you put locks in there, that you sort of thought about it. This is finding races that you forgot about rather than races that you ostensibly thought about. And there's some races that are actually correct. For example, in the chess program, there's this big table that remembers all the chess positions that have been seen. And if you don't get the right answer out of the table, it doesn't matter because you just search it again anyway. Not getting the right answer means you don't get any answer. You look something up and it's not there, so you search again. And if you just waited a little longer, maybe somebody else would have put the value in, you could have saved a little work. And so in that case, well, it turns out to be there's no parallel way to do that. So you say, well, I'm willing to tolerate that race because that gives me performance. And so we have what we call fake locks, which are basically things that look like lock calls, but they don't do anything except tell the race detector, pretend that there was a lock held in common. Yeah?
And the detection of races does not depend on the Cilk scheduler? So I mean, if you report a race on 10 processors, will you definitely report a race on 5 processors? It seems like you'll be serializing some code.
It tells you about, if it says there's no race, it means that for every possible scheduling,
Then you kind of have to unfold the spawns too.
well, so you have that DAG, and imagine running it on one processor. There's a lot of possible orders in which to run the DAG, right? And the rule is, well, was there a load and a store, or a store and a store that switched orders in some possible schedule? And that's the definition.
So in practice, one of the most significant techniques to getting performance, right, is lock-free synchronization. And assuming, depending on the processor, that you have atomic reads, you have atomic writes, you read one to deal with that data, if it gets written to in the background while you're dealing with it, no problem, right?
Those protocols are really hard to get right, but yes, it's a important trick.
Certainly engaged.
So to convince the race detector not to complain, you put fake locks around it.
Okay,
right?
those,
And then you have to, you've programmed a sophisticated algorithm. It's up to you to get the details right. Right. This is just trying. This is. Yeah. So the other property about this race detector is that it's fast. It runs almost in linear time. A lot of the race detectors that you find out there run in quadratic time. So if you want to run 1,000,000 instructions, it has to compare every instruction to every other instruction. It turns out we don't have to do that. We run in time, which is n times alpha of n, where alpha is the inverse Ackermann function. Anybody remember that from the union find algorithm? It's hard that, it's got that buried in it. So it's like the almost linear time. And we actually now have a linear time one that is even, has some performance advantages. So let me do a little theory and practice. In Cilk, we have some fundamental complexity measures that we worry about. So we're interested in knowing and being able to predict the runtime of a Cilk program on P processors. So we want to know T sub P, which is the execution time on P processors. That's the goal. What we've got to work with is some directed acyclic graph that, at least for a particular input set, and if the programs determine it and everything else, it's a well-defined graph. And we can come up with some basic measures of this graph. So T1 is the work of the graph, which is the total time it would take to run that graph on one processor. Or if you assume that these things are all cost unit time, it's just the number of nodes. So for this graph, what's the work? I heard teen, but something. 18? Let's see. And the critical path is the longest path. And if these nodes weren't unit time, you have to weight the things according to actually how much time they run. So the critical path here is what? 9. So I think those are right. The lower bounds then that you know is that you don't expect the runtime on P processors to be faster than linear speedup. In this model, that doesn't happen. Now, it turns out cache does things. It's adding more than just processors, right? You're adding more cache too, and so all sorts of things. Or maybe it means that there's a better algorithm you should have used. So there's some funny things that happen if you have bad algorithms and so forth. But in this model, you can't have more than linear speedup. You also can't get things done faster than in linear time. This model assumes basically that these costs of running these things are fixed, and the cache has the property that changing the order of execution means that the actual costs of the nodes in the graph change costs. So those are lower bounds. And the things that we want to know are speed up. So that's T1 over TP. And the parallelism of the graph is T1 over T infinity. So the work over the critical path. And we've been calling this span sometimes lately. Some people call that depth. Span is easier to say than critical path. Depth has too many other meanings, so I kind of like span. So what's the parallelism for this program? 18 over 9. You guys, you said that T1 was what? 18. T infinity is 9. So on average, and if you had an infinite number of processors and you scheduled this as greedy as you could, this is, it would take you 9 steps to run, and you would be doing 18 things worth of work. So on average, there's 2 things to do. 1 plus 1 plus 1 plus 3 plus 4 plus 4 plus 2 plus 1 plus 1 divided by 9 turns out to be 2. So the average parallelism, or just the parallelism of the program, is T1 over T infinity. And this property is something that's not dependent on the scheduler. It's a property of the program. It doesn't depend on how many processors you have.
So like a side note, you're saying you're calling that a span now?
Yeah.
One for us, I guess, just locally, we're sort of stealing terminology from compilers and generally call those traces. So in this case, we'd say the longest trace.
But that's too long to say, right? I might as well say critical path length.
But just
right? Critical path length, longest trace, span is a mathematical sounding name.
we
So.
just like to steal terminology.
Well, yeah. So there's a theorem due to Graham and Brent that says that there's some schedule that can actually achieve the sum of those two lower bounds. This linear speedup is one lower bound of the runtime, and the critical path was the other. So there's some schedule that basically achieves the sum of those. And how does that theorem work? Well, at each time step, either, suppose we had 3 processors, either there's at least 3 things ready to run. And so what you do is you do a greedy schedule. You grab any 3 of them, right? If there's fewer than p things to run, like here we have a situation where these have all run. The green ones are ready to go. And those are the only 2 that are ready to go. So what do you do then in a greedy schedule? You run them all, right? And the argument goes, well, how many time steps could you execute 3 things? At most, you could do it the work divided by the number of processors times, right? Because then after that, you've used up all the work. Well, how many times could you execute less than p things? Well, every time you execute less than p things, you're reducing the length of the remaining critical path. So you can't do that more than the span times. And so a greedy scheduler will achieve some runtime which is within the sum of these 2. It's actually the sum of these 2 minus 1. It turns out that there has to be at least one node that's on both work and critical path. And so that means that you're guaranteed to be within a factor of 2 of optimal with a greedy scheduler. And it turns out that if you have a lot of parallelism compared to the number of processors, so if you have a graph that has 1,000,000-fold parallelism and 1,000-fold processors, well, if this is really small compared to the work, right? If you have a graph with 1,000,000-fold parallelism, that means the critical path is small. If you only had 1,000 processors, that means this term's big. And that means that this term is very close to this term. So essentially, the corollary to this is that you get linear speedup, perfect linear speedup, asymptotically, if you have fewer processors than you have parallelism in your program. So the game here, at this level of understanding, we haven't told you how the scheduler actually works, is to write a program that's got a lot of parallelism so that you can get linear speedup. Okay? Well, the work-stealing scheduler we actually use, the problem is the greedy schedulers can be hard to compute, especially if you imagine having 1,000,000 processors in a program with 1,000,000,000-fold parallelism. Finding on every clock cycle, finding something for each of the 1,000,000 guys to do is conceptually difficult. So instead, we have a work-stealing scheduler, and I'll talk about that in a second. It achieves bounds which are not quite as good as those there. This bound is the same. It's the sum of 2 terms. One is the linear speedup term, but instead of it being t infinity, it's big O of t infinity. Because you actually have to do communication sometimes if the critical path length is long. Basically, you can sort of imagine if you have a lot of things to do, a lot of tasks and people to do it, it's easy to do that in parallel if there's no interdependencies among the tasks. But as soon as there's dependencies, you end up having to coordinate a lot, and that communication costs, there's this, lots of lore about adding programmers to a task and it slowing you down, right? Because basically the communication gets you. What we found empirically, there's a theorem for this. Empirically, the runtime is actually still very close to the sum of those terms. Or maybe it's those terms plus 2 times t infinity or something like that. And again, we basically get near perfect speedup as long as the number of processors is a lot less than the parallelism. It should be sort of a less than. And we provide the compiler. The compiler has a mode where you basically can insert instrumentation, so you can run your program. It'll tell you the critical path length. You can compute these numbers, right? You can see clear how to compute work. You just sum up the runtime of all the threads. To compute the critical path length, well, you have to do some maxes and stuff as you go through the graph. And the average cost of a spawn these days is about 3 on a dual-core Pentium, 3 times the cost of a function call. And most of that cost actually has to do with the memory barrier that we do at the spawn, because that machine doesn't have strong consistency. So you have to put this memory barrier in, and that just empties all the pipelines. It's it does better on like an SGI machine, which has strong, well, a traditional, a MIPS machine that has strong consistency actually does better for the cost of that overhead. So let me talk a little bit about chess. And we had a bunch of chess programs. I wrote one in 1994, which placed third at the International Computer Chess Championship, and that was running on a big connection machine, CM5. And I was one of the architects of that machine, so it was double fun. We wrote another program that placed second in 95, and that was running on an 1800 node Paragon, and that was a big computer back then. We built another program called Cilk Chess, which placed first in 96, running on a relatively smaller machine. And then on a larger SGI origin, we ran some more. And then at the World Computer Chess Championship in 1999, we beat Deep Blue and lost to a PC. And people don't realize this, but that at the time that Deep Blue beat Kasparov, it was not the World Computer Chess Champion. A PC was. So, what? It's running a program. So, you know, there's this head and a tape. And I don't know what it did. So this was a program called Fritz, which is a commercially available program. And those guys were very good. You know, the PC guys were very good at getting on sort of the algorithm side. You get some, you know, we got advantage by brute force, and we also had some real chess expertise on our team. But those guys were spending full time on things like pruning away sub searches that they were convinced weren't going to pan out. Computer chess programs spend most of their time looking at situations that any person would look at and say, black's won. Why are you even looking at this? And it keeps searching, you know. It's like, well, maybe there's a way to get the queen, you know. And it could be that. So computers are pretty dumb at that. So basically, these guys put a lot more chess intelligence in, and we also lost due to what in this particular game we were tied for first place, and we decided to do a runoff game to find out who would win, and we lost due to a classic horizon effect. So it turns out that we were searching to depth 12 in the tree, and Fritz was searching to depth 11. Even with all this heuristics and stuff they had in it, they were still not searching as deeply as we were. But there was a move that was a good move that looked okay at depth 11 and looked bad at depth 12, and at depth 13, it looked really good again. So they saw the move and made it for the wrong reason. We saw the move and didn't make it for the right reason, but it was wrong. And the right move, if we'd been able to search a little deeper, we would have seen that it was, you know, really the wrong thing to do. So it's you know, this happens all the time in chess. There's a little randomness in there. This horizon effect shows up. And again, it boils down to the programs are not intelligent. A human would look at it and say, eventually that knight's going to fall. But if the computer can't see it with a search, you know. So we plotted the speed up of star Socrates, which was the first one, on this funny graph. So this looks sort of like a typical linear speed up graph. Sort of when you're down here with few numbers of processors, you get good linear speed up, and eventually you stop getting linear speed up. That's sort of, in broad strokes, what this graph looks like, right? But the axes are kind of funny. The axes aren't the number of processors, and the speed up, it's the number of processors divided by the parallelism of the program. And here it's the speed up divided by the parallelism of the program. And the reason we did that is that each of these data points is a different program with different work and span. And so if I have a different, you know, if I'm trying to run a particular problem on a bunch of different processors, I can just draw that curve and see what happens as I get more processors. I no longer need, you know, I'm not getting any advantage because I've got too many processors. I've exceeded the parallelism of the program. But if I'm trying to compare two different programs, how do I do that? Well, you can do that by normalizing by the parallelism. So down in this domain, the number of processors is small compared to the average parallelism, and we get good linear speedups. And up in this domain, the number of processors is large, and it starts asymptoting to the point where the speedup approaches the parallelism. And that's sort of what happens. And you get some noise out here. So one of the things down here, it's nice and tight, right? And that's because we're in that domain where the communication costs are infrequently paid, because there's lots of work to do. You don't have to communicate very much. Up here, there's a lot of communication that happens, and so the noise is showing up more in the data. So it's like this curve here is the T1 over P plus T infinity curve. And that's the P equals T infinity curve, and that's the linear speed up curve on this graph. So so I think there's an important lesson in this graph besides the data itself, which is if you're careful about choosing the axes, you can take a whole bunch of data that you couldn't see how to plot it together, and you can plot it together and get something meaningful. So in my PhD thesis, I had hundreds of little plots for each chess position, and I didn't figure out how. It's like they all look the same, right? But I didn't sort of figure out that if I was careful, I could actually make them be the same. That happened after I published my thesis. Oh, we could just overlay them. And, well, what's the normalization that makes that work? So there's a speed-up paradox that happened. Pardon?
Oh, this is a countdown.
Yeah, okay. There was a speed-up paradox that happened while we were developing Star Socrates. We were developing this for a 512 processor connection machine that was at University of Illinois, but we only had a smaller machine on which to do our development. We had a 128 processor machine at MIT, and most days I could only get 32 processors because the machine was in heavy demand. So we had this program, and it ran on 32 processors in 65 seconds, and one of the developers said, here's a variation on the algorithm. It changes the DAG. It's a heuristic. It makes the program run more efficient. Look, it runs in only 40 seconds on 32 processors. And so he says, is that a good idea? And it sure seemed like a good idea. But we were worried that we knew that the transformation increased the critical path length of the program, so we weren't sure it was a good idea. So we did some calculation. We measured the work and the speed up. And so the work here, and these numbers have been cooked a little bit to make the math easy, but the numbers, this really did happen, but not with these exact numbers. So we had a work which was 2,048 seconds and only 1 second of critical path, and over this new program had only half as much work to do, but the critical path length was longer. It was 8 seconds long. So if you measure it on if you predict on 32 processors what the runtime is going to be, that formula says, well, 65 seconds. And if you predict it on 32 processors well, it's 40 seconds, and that looked good, but we were going to be running the tournament on 512 processors, where this term would start being less important than this term. So this really did happen, and we actually went back and validated that these numbers were right after we did the calculation, and it was like it allowed us to do the engineering to make the right decision and not be misled by something that looked good in the test environment. We were able to predict what was going to happen on the big machine without actually having access to the big machine, and that was very important. Let me do some algorithms. You guys probably have done some matrix multiplies over the past 3 weeks, right? That's probably the only thing you've been able to do, should be my guess. So matrix multiplication is this operation. I won't talk about it, but you know what it is. In Cilk, instead of doing the standard triply nested loops, you do divide and conquer. We don't parallelize loops, we parallelize function calls. So you want to express loops as recursion. So to multiply two big matrices, you do a whole bunch of little matrix multiplications of the subblocks, and then you express those little matrix multiplications themselves, go off and recursively do smaller matrix multiplications. So this requires 8 multiplications of matrices of half the number of rows and half the number of columns, and 1 addition at the end where you add these 2 matrices together. That's the algorithm that we do. It's the same total work as the standard one, but it's just expressed recursively. So matrix multiply is, you do these 8 multiplies. I had to create a temporary variable. So the first 4 multiply the A's and B's into C. The second 4 multiply the A's and B's into T, and then I have to add T into C. So I do all those spawns, do all the multiplies. I do a sync, because I better not start using the results of the multiplies and adding them in until the multiplies are done. Then I do, what? There's parallelism in add, right? Matrix addition.
Yeah, but doesn't add spawn itself? I mean,
Well, we spawn off add. I don't understand this.
But what's running in parallel with that?
yeah, there's nothing running parallel with add in
So you have to spawn Cilk functions even if you are only executing one of them at a time. Okay? Right. Cilk functions are spawned, C functions are called. It's a decision that's built into the language. It's not really a fundamental decision. It's just, that's the way we did it.
Why did you choose to have the keyword then? That's just documentation from the caller side?
Yeah, we found that it made our code we were less likely to make a mistake if we sort of built it into the type system in this way. But I'm not convinced that this is the best way to do this type system.
Can a C function spawn a Cilk function?
No. You can only call spawn, then you can call C functions at the leaves. It turns out you can actually spawn Cilk functions if you're a little clever about it. There's a mechanism there's a Cilk system running in the background, and if you're running C, you can say, okay, do this Cilk function in parallel. So we have that, but that's not didactic, So.
I have a question about the sync and spawn immediately after. Is the sync actually doing a full wait, or like in the case of maybe not in the case of the add here, but in plenty of other practical functions, right? You get inside the spawn function looking at the dependencies of the parameters, right, based on how those were built from the previous spawn functions. You can actually just start processing so long as it's guaranteed that the results are available before you actually read them.
So there's this other style of expressing parallelism which you see in some of the data flow languages where you say, well, I've computed this first multiply, why can't I get started on the corresponding part of the addition, right? And it turns out that in those models there's no performance guarantees. The real issue is you run out of memory. So it's a long topic. Let's not go into it. But there's a serious technical issue with those programming models. Is that we only use we have very tight memory bounds as well. So we simultaneously get these good scheduling bounds and good memory bounds. And if you are doing that, you could have sort of a really large number of temporaries required and run out of memory. The data flow machines used to have this number. There was the student Ken Traub who was working on Monsoon when Greg Papadopoulos was here, and he came up with this term which we called Traub's constant, which was how long the machine could be guaranteed to run before it crashed from being out of memory. And that was, well, you took the rate at which it could cons, divide it by the amount of memory, and that was it. And many data flow programs had that property. It's like the Monsoon could run for 40 seconds, and then after that, you never knew. It might start crash at any moment. So everybody wrote short data flow programs. So one of the things you actually do when you're trying to engineer this to go fast is you coarsen the base case, which I didn't describe up there. You don't just do a one-by-one matrix multiply down there at the leaves of this recursion. Because then you're not using the processor pipeline efficiently. You call the Intel math kernel library or something on a 8x8 matrix so that it really gets the pipeline a chance to chug away. So analysis. This matrix addition operation, well, what's the work for matrix addition? Well, the work to do a matrix operation on n rows is, well, you have to do 4 additions of size n over 2, plus there's order 1 work here for the sync. And that recurrence has solution order n squared. Well, that's not surprising. You have to add up 2 matrices, which are n by n. That's going to be n squared, so that's a good result. The critical path for this is, well, you have to do all of these in parallel, so whatever the critical path of the longest one is, they're all the same, so it's just the critical path of the size n over 2 plus order 1, so the critical path is order log n. For matrix multiplication, sort of the reason I do this is I can, right? It's like this is a model in which I can do this analysis, so I have to do it, right? But it really, being able to do this analysis is important when you're trying to make things run faster. Matrix multiplication, well, the work is I have to do 8 little matrix multiplies, plus I have to do the matrix add. So the work, the work has solution order n cubed, and everybody knows that there's order n cubed multiply adds in a matrix multiply, so that's not very surprising. The critical path is, well, I have to do a add, so that takes log n, plus I have to do a multiply on a matrix that's half the size. So the critical path length of the whole thing has solution order log squared n. So the total parallelism of matrix multiplication is the work over the span, which is n cubed over log squared n. So if you have a 1,000 by 1,000 matrix, that means your parallelism is close to 10 million. So there's a lot of parallelism. And in fact, we see perfect linear speedup on matrix multiply because there's so much parallelism in it. It turns out that this stack temporary that I created so that I could do these multiplies all in parallel is actually costing me work because I'm on a machine that has cache and I want to use the cache effectively. So I really don't want to create a whole big temporary matrix and blow my cache out if I can avoid it. So I propose the following matrix multiply, which is I first do 4 of the matrix multiplies into C1, then I do a sync, and then I do the other 4 into C1, and another sync. And I forgot to do the add. Oh, no, those are multiply adds. So they're multiplying and adding in. And this saves space because it doesn't need a temporary, but it increases the critical path. So is that a good idea or a bad idea? Well, we can answer part of that question with analysis. Saving space we know is going to save something. But what does it do to the work in critical path? Well, the work is still the same. It's n cubed because we didn't change the number of flops that we're doing. But the critical path has grown. Instead of doing 1 times a matrix multiply, we have to do 1 and then sync and then do another one. So it's 2 matrix multiplies of half the size plus the order 1. And that recurrence has solution order n instead of order log squared n. So that sounds bad. We've made the critical path longer. What? Yeah. So parallelism is now order n squared instead of n cubed over log squared n. And for a 1,000 by 1,000 matrix, that means you still have a millionfold parallelism. So for relatively modest-sized matrices, you still have plenty of work to do this optimization. So this is a good transformation to do. And one of the advantages of Cilk is that you can do this kind of transformation. You can say, well, let me do an optimization. And I could do an optimization in my C code, and I get to take advantage of it in the Cilk code. Or I could do this kind of optimization of trading work for parallelism if I have a lot of work. That sometimes is a good idea. Ordinary matrix multiplication just is really bad. Basically, you can imagine spawning off the n squared inner dot products here and compute them all in parallel. It has work n cubed, parallelism log n, so it has, critical path log n, so the parallelism is even better. It's n cubed over log n instead of n squared. So that looks better theoretically, but it's really bad in practice because it has such poor cache behavior. So we don't do that. I'll just briefly talk about how it works. So Cilk does work stealing. We have this double-ended queue, or deck. So at the bottom of the queue is the stack where you push and pop things, and the top is something where you can pop things off if you want to. And so what's running is all these processors are running each on their own stack. They're all running the ordinary serial code. That's sort of the basic situation. They're pretty much running the serial code most of the time. So some processor runs, it pushes, well, it does a spawn, so what does it do? It pushes something onto its stack, because it's just a function call. And it does a couple more spawns, so things pop off. Somebody returns, so he pops his stack. So far, everything's going on. They're not communicating. They're completely independent computations. This guy spawns, and now he's out of work. Now he has to do something. What he does is he goes and picks another processor at random, and he steals the thing from the other end of the stack. So he's unlikely to conflict, because this guy's pushing and popping down here. But there is a lock in there. There's a little algorithm. A non-blocking algorithm, actually. It's not lock. And so he goes and he steals something, and come on, slide over there. Whoa, yes, that's animation, right? That's the extent of my animation. And then he starts working away. And the theorem is that a work-stealing scheduler like this gives expected running time with high probability, actually, of T1 over P plus T infinity on P processors. And the pseudo-proof is a little bit like the proof for Brent's theorem, which is either you're working or stealing. If you're working, well, that goes against T1 over P. You can't do that very much, or you run out of work. If you're stealing, well, each steal has a chance that it steals the thing that it's on the critical path. You may actually steal the wrong thing, but you actually have a 1 in P chance that you're the one who steals the thing that that it's on the critical path, and in which case the expected number, so you have this chance of 1 over P of reducing the critical path length by 1, so after this many steals, the critical path is all gone. So you can only do P over T and P times T infinity steals with high probability, it turns out. And that gives you these bounds. Okay, I'm not going to give you all this stuff. It's message passing sucks, you know. You guys know this stuff. Come on. There's probably nothing else in here. So basically, the pitch here is that you get some high-level linguistic support for this very fine-grained parallelism. It's an algorithmic programming model, so that means that you can do engineering for performance. There's fairly easy conversion of existing codes, especially when you combine it with the race detector. You've got this factorization of the debugging problem into debugging your serial code. As you run it with all the Cilk stuff turned off, you elide the program and make sure your program works. Then you run it with the race detector to make sure you get the same answer in parallel, and then you're done. Applications in Cilk don't just scale to large number of processors, they scale down to small numbers, which is important if you only have 2 processors or 1. You don't suddenly want to pay a factor of 10 to get off the ground, which happens sometimes on clusters running MPI. You have to pay a big overhead before you've made any progress. And one of the advantages, for example, is that the number of processors might change dynamically. In this model, that's okay because it's not part of the program. So you may have the operating system reduce the number of actual worker threads that you have doing that work stealing, and that can work. One of the bad things about Cilk is that it doesn't support sort of data parallel or program model kind of of parallelism. If you really have to think of things as this divide and conquer kind of the world, and if you have trouble expressing that, so situations where you're doing Jacobi update and you've very carefully put things on, had each processor work on its local memory, and then they only have to communicate at the boundaries. That's difficult to do right in Cilk because essentially every time you go around the loop of I have all these things to do, all the work stealing happens randomly and it happens on a different processor. So it's not very good at that sort of thing, although it turns out Jacobi update's not a very good example for that because there are more sophisticated algorithms that use cache effectively that you can express in Cilk, and I have no idea how to say those in some of these sort of data parallel languages. And using the cache efficiently is really important on modern processors.
Good, thank you. Questions?
You can download Cilk. There's a bunch of contributors. Those are the silkworms. And you can download Cilk off our webpage. Just Google for Cilk and you'll find it. It's a great language. You'll love it. You'll love it much more than what you've been doing.
How does the Cilk play with processor-specific instructions like Intel SSE and something like that?
Well, you have to have a language that a compiler that can generate those. So if you have an assembly command or you have some other compiler that can generate those. So I just won the HPC challenge, which is this challenge where everybody tries to run their parallel programs and argue that they get productivity. For that, there were some codes like matrix multiply and LU decomposition with pivoting. Basically, at the leaves of the computation, I called the Intel math kernel library, which in turn uses the SSE instructions. So that you can do anything you can do in C in the C parts of the code because the Cilk compiler just passes those through. And so if you have some really efficient pipelined code for doing something, up to some point it makes sense to use that because you.
What did you run to win this competition, and what did you run it on?
So I ran it on NASA's Columbia.
What's it?
So the benchmark consists of there's 7 applications they have, 6 of which are actually well defined. One of them is this thing that just measures network performance or something, so it doesn't have any real semantics. So there's 6 benchmarks. One of them is LU decomposition, one of them is DGEM, matrix multiplication, and there's FFT and 3 others. So I implemented all 6, and nobody else implemented all 6. It turns out that you had to implement 3 in order to enter. And almost everybody implemented 3 or 4, but I did all 6, which is part of why I won, because I could argue that in a week's work I just implemented.
What's it measuring? What's it measuring? So productive.
So the prize has 2 components: performance and productivity, or elegance, or something. And it's completely whatever the judges want that to be. So it was up to me as a presenter to make the case that I was elegant, because I had my performance numbers, which were pretty good. And it turned out that the IBM entry for X10 did me more good than I did, I think, because they got up there and they compared the performance of X10 to their Cilk implementation, and their X10 thing was almost as good as Cilk. So after that, I think the judges said they had to give me the prize. So basically, it went down to supercomputing, and each of us got 5 minutes to present, and there were five finalists, and we did our presentation, and then they gave out they gave the people at they divided the prize 3 ways. The people who got the absolute best performance, which were some people running UPC, and the people who had the most elegance based on minimal number of lines of codes. And that was Cleve at, what's his name, the MathWorks guy, the MATLAB guy, who said, look, matrix, LU decomposition, LU of P. And it's like, so it's very elegant, but I don't think that it really sort of explains what you have to do to solve the problems. So he won the prize for most elegance, and I got the prize for best combination, which they then changed in the final citation for the prize. They said most productivity. That was the prize. So I actually won the contest because that was what the contest was supposed to be, was most productivity. But I only won 1/3 of the prize money because they divided it 3 ways.
Any other questions? Okay, good. Thank you.
Thank you for.
Finally bread, and since we had guest lectures, I didn't have a mini quiz for this day, so you can relax a little bit, look at the weather outside, and then basically. Why are you up?